In this video, we're going to be working with one particular cell process known as passive transport. Now, passive transport is just simply the movement of particles. And so we're thinking about moving across that cell membrane that our last video was about without, and this is the key, without the use, as I make a mistake already, of energy. So we're talking about we're moving particles, like I said, across that cell membrane, but we need no energy. Now, there's three ways that passive transport occurs, and so let's dive into our first way, and that is known as diffusion. Now, diffusion will not use energy. That's why it's labeled a passive transport action. But what's going to happen is these particles are going to move from an area of high concentration. Now keep in mind, concentration means amounts, as I try and squeeze in that word, okay, to low concentration. So we are talking about particles, so like polar or non-polar molecules, okay, or just different ions. They're going to be moving from high to low. Now, this difference in gradient, so let me show you what I mean. Here's our cell membrane. Notice there's a lot of these circles, particles in one area and not so many on the other area. This is known as a gradient. And so it's called a concentration gradient. This is simply a difference in the particle amount. And you saw that in that image. So we have, so based by diffusion, what you just wrote down, if we have a high amount on one side of the cell membrane, those particles are going to move to the other side where there's a low amount. And they're simply just going to diffuse or move across that membrane. Now, this movement doesn't just happen one time, okay? This is going to occur when the molecules are going to collide with one another. And over time, as these particles move from high to low, you can kind of see in this image, they're moving from high to low. They're going to reach an equilibrium. Now, this equilibrium, though, is always changing. So I'm going to make sure we get that down. So molecules will keep moving. But here's the key, the concentrations, the amounts will remain equal, will remain the same. And so this is what we call equilibrium. So usually when people think of equilibrium, it means, okay, we've gotten 5 and 5 on each side and that's it. But that's not it. It's a constant movement, a constant collisions going into each other, but it's a balanced concentration on both sides. Now, some examples of this, if you've ever tie-dyed a shirt before, this is how tie-dye works. Think about it. When you tie-dye, you roll your shirt up, okay? You put your ink blots wherever you want it. The dye particles are concentrated in an area, but then you got to let your shirt sit for about 24 hours. And you'll notice that those molecules will move from the dye or the concentrated area to the less concentrated area, okay? And so as the dye spreads out, it's still moving and you get those lovely patterns. It's going to reach an equilibrium. This also occurs when we're trying to move carbon dioxide and oxygen in and out of your cells, because remember, we breathe in oxygen, we breathe out carbon dioxide. And so these molecules are just going to be diffused, no energy needed, across these cell membranes. Now, a second type of passive transport is known as facilitated diffusion. Now, it's very similar to the process we just went through, except facilitated means there needs to be a helper. It means that these molecules cannot move directly across the membrane. So instead of just simply slipping through the membrane, they need a helper. And so they need to pass through special protein channels. And that's their helpers are these protein channels, and that's why it's called facilitated, because facilitated, like I said, means helper, okay? And so these protein channels only allow certain particles or certain molecules to pass. But just like diffusion, these molecules will move from areas of high concentrations to low concentrations or low amounts. And then they're also trying to reach that equilibrium. So let me kind of show you the facilitated, okay? It's like a door. It's like a door and a key. If the ion is not a certain molecule, so like here we have a square. So here we have a high amount of particles. And here we have a low amount of particles. So obviously, we're going to be moving across this membrane, but we just can't slip through the membrane. They're not the right size, or they're not the right shape. Maybe they're too big, or maybe they don't have the right sort of charge on them. So we're going to be having to use a facilitated diffusion process or these protein channels. This right here, this big purple blob, that's a protein channel. And so what they're going to be moving across, a good example of facilitated diffusion, would be when we're trying to exchange sodium and potassium through our cell membrane. And so when the sodium ion passes through the channel, and by channel I mean the protein channel. You could also think another good example could be enzymes. We learned about that in our last unit. Proteins that act as biological catalysts. Enzymes are going to need to connect and to come across, carry in their whatever sort of ion they're trying to, or substrate they're trying to change into a product. So this is facilitate diffusion. No energy, still going from high to low amounts, but we need something to help us get across that cell membrane. All right, and I said there's 3 of them. We're on our last one. Third one is known as osmosis, the third type of passive transport. Now, Osmosis Jones, that's a movie. We're talking about osmosis, the process. Now, this is simply referring to the movement of water across that cell membrane. Now, this water is still going to move from areas of high amounts to low amounts or concentrations. And this is kind of key because we're talking about not just water, but we're also talking about particles that dissolve in water. Remember that word solute, particles that dissolve in water. So the higher the amount of particles in a solution means that you have lower amounts of water. So like think about it. If you put a lot of sugar in a cup of water, there's not going to be as much water in that cup. Okay, so a lot of particles, little bit amount of water. This is something to really keep in mind because osmosis isn't just one singular process when we're talking about movement of water. There's 3 ways that cells are affected, and that's what we're going to get into. So the first way is known as isotonic solution. And so this is when the cell has same amounts or same concentration of these dissolved particles. So when we're talking about particles, we could be talking about the sodium ions, or we could be talking about potassium ions, so dissolved particles. It just depends on what the cell is using and what its function is being. And so what does that mean? Because remember, it's about osmosis. We're talking about water movement. It means there's an equal amount of water that will enter or even exit the cell. And so what this is referring to, so what happens to the cell ultimately, it's going to stay the same size. So that's an example of, I show a picture here, Okay, isotonic means water's going in as the same time as water's going out. Okay, because there's particles in the cell and there's particles outside the cell and they're the same too. So just a normal, I would call it happy cell, I guess you want to think about it. Now, the second way that cells are affected by osmosis is known as hypertonic solution. So what's going to happen is there's a higher concentration or a higher amount of these dissolved particles in the solution around the cell. Okay, and so what that means for water movement, it simply means that more water will leave the cell, because remember, water moves from high amounts to low amounts. Okay, so let me kind of explain this a little bit. So more water is going to leave the cell because in our cell, okay, we have some particles inside the cell, but then we have a lot of particles, these are my particles, outside of the cell. Okay, but you got to think about it. If we don't have very many particles, I'm going to try and change to color blue because blue is water. So we have a lot of water inside the cell, lots, because there's not as many particles, lots and lots of water. And out here, we don't really have that much water because most of that space or area has these dissolved particles. So if we go from high to low amounts, this water is actually going to leave the cell because osmosis means water is traveling from the higher amounts to the lower amounts. So what that means for my cell, not a good thing, okay? This means that the cell is going to shrink or get smaller in size, which can ultimately leave the cell to maybe even die. Okay, so let's kind of look at this blood cell, or not blood cell, just a cell over here. Okay, this is hyper. So notice that not as many particles inside, a lot on the outside. So the water is going to go from the higher amount of water, which is inside, to the lower amount. So it's going to cause that cell to change shape. So you can kind of see the picture. It doesn't look as full and as plump as the isotonic one. Okay. All right, but we're not done yet. We have hypertonic. So now let's look at the third kind, which is hypotonic. It's just the opposite of what we were kind of looking at above. Okay. So what this means is that there is a lower amount of these particles in the solution around the cell, so outside of cell. So that means there's a higher amount inside. So let me get my little picture going. I'm going to draw my cell again. So here's my awesome cell. Okay. Oh, that was a fun picture. Mrs. Ellis is not the best drawer. Please note that, and it is okay. All right, so here's my cell. So there's a lot of particles in here. Lots and lots and lots and lots and lots, filling up all this space. So trying to get my little particles going. But then outside the cell, there's a lower amount. So if we think about water, not so much water is taking up the inside of the cell, but there's lots of water outside of my cell. Look at all that water. Okay, so I'm going to put lots, I was going to say more of water outside cell. So what direction? Think about it. If water is moving from high amounts to low amounts, the water is going to move from the outside to the inside of the cell. So water moves outside to inside the cell. So what does that mean for the cell? Because that's ultimately what we want to see what's it affecting. The cell is going to get larger in size. It's going to expand. because it's filling up full of water. Duh. Okay. But if it gets too much water inside, think about too much air in a balloon, the cell could actually eventually burst. So this is not a great condition either. So let me show you this one, okay? Hypotonic, the cell's going to get much bigger in size. It's going to look very large and squishy, okay? So let's take these 3 words about osmosis, because I think these get very commonly mixed up, and let's apply it here, okay? So in these images, it's kind of showing you the direction of water that's occurring. So let's look at the middle one first. Notice that same amount of water is entering as it's exiting because of the particles. Okay, and so hopefully you're thinking this middle picture is the isotonic. Okay, all right, now let's look at this first one. A lot of water is leaving, so that means inside there's high amounts of water. Okay, outside there's low amounts of water because it's all about those particles. And so if we're going to move from high to low, water is going to leave the cell. Then we're looking at a hypertonic solution. Okay. Now let's look at this other picture. Outside the cell, going to inside the cell. We're going from high amounts to water to low amounts of water. So the cell's going to fill up. It's going to get much, much bigger in size, practically almost burst maybe. So this is hypotonic solution. So in this video, we simply just covered ways that particles can move across the cell membrane without water.